a week or two long and then start collecting data on it. The more data, the better the quality of the analysis that you'll be able to do on that data. Any questions on this? I think this blue stuff is the only stuff that I added here, so, oh yeah, no, that's still pretty much the same. Again, don't change your 3 flights, and you'll be turning in a Microsoft Word document. You might take a look at the document after you've handed it in. It's in database class that I notice with the data-heavy graphs that I have people generate, where the translation from a Microsoft Word document to a PDF document, which is what D2L does in the background by default, whether you ask for it or not. Sometimes the lines shift in the final graphs, and so the graph that you turned in and that you described doesn't actually fit your description anymore. That has happened, but usually with large amounts of data. We're probably not there yet, but in a later assignment when we've got 1,000 points or something that we're drawing lines through or illustrating with lines, it might happen. And they might have fixed that since then. I don't know. Any questions? What were we talking about in this class on Wednesday?
Good database operators, like union.
Yeah, so basically some mathy operators that do database things. I think I'll start a couple of slides back here. Grab a clicker that once again I will not know how to use. So we were talking about natural join. Can anyone remind me what a natural join is again, as illustrated apparently by this bow tie operator that takes these 2 separate tables and blends them into one table? How can you explain the blending that is going on? Does it make sense? Give it to me, Preston. What's going on here?
Trying to remember here.
I see a bunch of alphas in my resulting table, that column A. Where did all my betas and twiddles and deltas go? Gammas, I guess, and deltas. Did I have an example? I think that here's my example. I have these 2 tables here, and I want to join them up, and I guess the natural join method is it's just going to look at column names and assume that column names mean the same thing wherever you see them. So B means B and D means D, and so if you see an alpha or I guess if you see a 1 or a 2 or a 4 in the B column, and that means number of people at your pizza party, then in the other table in column B, 1 and 3 and 1 are also talking about number of people in the pizza party. They're not only the same data type, but they also have the same meaning. And same thing for D, A, B, and the lowercase letters A and B also mean the same thing no matter where they are in which table, as long as those columns have the same names. And so the natural join of those 2 tables, R and S, is a new table, a new relation, whose schema is the union of R and S. That is, it has all of the column names from both of the tables, and it actually also eliminates the duplicate column names as part of the union operation, because that's how the mathematicians like it. And basically, in this combined table of column names, so A, B, C, D, and E would be the only non-duplicate there. We would see combined values from these combined rows, but only for every pair of rows, T sub R and T sub S, R coming from the R table and S coming from the S table, where TR and TS have the same value on each of the column names that are common between the two tables, right? So the two column names are common between these two tables are B and D, and so if this row were to make it into my A, B, C, D, E table, then it would have to be combined with a row from that table where the values in columns B and D were 1 and A, which luckily we seem to have, right? Same value in the B column, same value in the D column, so those two rows get concatenated together, and we're only going to show the B and D columns once. Those would just be duplicate values. Access shows all the duplicate columns, but it actually does save a little bit of space. Saves a little bit of us having to interpret with our eyes what's going on if we're not seeing duplicate columns. So I guess I agree with the mathematicians on that. And we've just combined the alpha from this row to the alpha 1 alpha A that came from the original row. And so there's that one. And then we also know that this guy is going to combine with this guy, right? And nobody else. So alpha 1 alpha A gamma. And so do we have any 2 A's in this table? No, so this row is not going to combine with anybody. Do we have any 4 B's? No 4 B's that I can see. This row isn't going to combine with everybody. The next row that combines with anybody is this 1A row. As we know, there's already 2 1A rows here. And so this row will combine with this row. We'll add an alpha onto the end of this here when it appears over there. Right? Alpha 1 gamma A alpha. And this row will also combine with this row. So it'll add a gamma at the end. Alpha 1 gamma A gamma. Right? And then is there a 2B to connect to? Yeah, there is in that other table. There's a 2B. So this row is going to combine with this row, and this delta will be added to the end of that in the resulting table, so that we have all unique columns in the resulting table, and their matching values from both sources that came together to join those two tables together. All right? So again, these 3 tables, we're going to replicate them on this slide here. Those are the 2 source tables. Now you saw how those tables blended together. Not every row contributed to this table. I mean, it's not a Cartesian product operator where every row connects to every other row. Although it did go through that phase, we just didn't force you to write out that massively huge and mostly useless table, because it only returned those rows that had matching values on the important columns. We know those columns are important merely because they have the same names, B and D. They are what drives the natural join process. So the symbol for that is the bow tie here. We know that table R will be joined with table S, but only those rows that have the same values on columns with the same names will actually concatenate and be returned in the resulting table. This is the biggest thing you want to learn about SQL. This is how all of your databases get joined together. This is these common values between tables are the glue that bind values together and allow you to combine a student with an instructor with a course that's being given during a time slot, and grab whatever values, whatever rows are appropriate from whatever tables they're in, and build some sort of table that makes sense on your computer screen in front of you, showing your schedule of classes for next semester. that's how that happens on the CS server that the McGee-State.edu website is using when you display your class schedule. Pulling values from various tables. Probably not exactly the same design as in the schema that I handed out. You might also want to pull out that schema that I handed out. But probably something that's not all that far from it either. Has a lot more columns in it that are incomprehensible to you, but they probably mean something to some administration drone up there in Deputy. So that's natural join. The only thing that I don't like about natural join is the assumption that that a column with the value name in one table is going to mean the same thing as another column in another table with the value name. Because I can see right from the schemas in front of you right now that instructor name does not mean the same thing as student name, right? I mean, they are the same data type, they're both strings, but they're not names of the same things. Usually, I'm not going to be able to join two tables on the name field and expect to get very much commonality that makes sense. I mean, if we have a student named Francois Neville running around campus out there, then my rows will be connected with their rows, but assuming they're a different person, that result won't make sense. So I would prefer a command that, doesn't put add the constraint that or that doesn't think that similar names mean similar data and similar meanings. And so that's where I think I may have ended class on last time here. Oh no, this is my second example. I think I ended my class on this slide last time. And this is where inner join comes from. It's like a generic version of natural join. And the symbol we're going to use for that, we're almost never going to use the bow tie, because bow tie says that name means name means name, and that's not going to be true most of the time. And so we're just going to go back to the old Cartesian product operator, and the only thing that we're going to change about it is we're going to add a predicate. We're going to add a rule to it. Oops. That says, we're going to combine every row with every row, but only keep those rows where the values are the same on these fields, and I can use different names there. And so, if you look at your schema, you've got a student table, and that student table has an ID field in it, right? And you've got an advisor table, and you can tell in your schema that advisor table has an S_ID field in it. And by the way, the student table does not have an S_ID column, and the advisor table does not just have an ID column. And so I don't need to prepend those column names with table names. I would if they both had IDs. I would say a student.id or instructor.id if I were trying to combine those two tables together. But if those names are unique to the table, then I'm not going to prepend them with anything. And usually, in a statement like this, if I'm just going to use the first letter of the table, most of the time, first letter will be unique between all the tables that I use. So I would say, if I had to prepend, I would say s.id and then a.s_id. And so that you know which table I'm grabbing that thing from. So yeah, what is this doing now? We're grabbing everything from student and we're combining it with everything from advisor, but we're only combining the student rows to the rows in the advisor where the student ID is the value is the same as the s_ID value in the advisor table. And so this works exactly like natural join. It's just working on differently named columns, but that's the only difference. It is going to return, what is the schema of student? It's going to return ID, name, and ID and name and department name and total credits and S underscore ID and I underscore ID. Remember, it does a union of all the column names. It builds a combined table. The student table has 4 columns in it. The advisor table has 2 columns in it. The resulting table from this will have 6 columns in it. Even if tables did have the same column names, we wouldn't follow the mathematicians and delete or uniquify the column names. We're going to pretend we're going to assume that in the real world we're going to keep everything. It's only when we're talking theoretically relational algebra operators that we talk about uniquifying column names, because we're also assuming that column name B means column name B wherever it comes from, and you can tell in this schema that's not true. So it joins together all the rows from the student table only with the rows from the advisor table that contains the ID of that particular student's advisor. So you'll have student names and their department names and I've already forgotten their IDs and their total credits, combined with, from the other table, the student's ID, and those 2 values should be the same, right? Because ID, the student ID, is actually a foreign key inside the advisor table. It is a value that came from the student table. They should be the same. And its name in the advisor table is actually S underscore ID, but it means the same thing. It is the ID of a student object. And then so we'll have an S underscore ID row in the resulting table, and then we'll have an I underscore ID column, not row. We'll have an I underscore ID column that contains the advisor's ID, and you can tell from the line drawn on your schema diagram that line connects from I underscore ID to the ID field in the instructor table. So you know what that means. Again, there's 2 columns named ID between student and instructor, but they don't mean the same thing. They're not IDs of the same entity, of the same object. So natural join would be a terrible choice for this database. We should use Cartesian product with these predicates. And so that's how inner join will be represented. It's not something that we consider to be a fundamental operation of relational algebra, but if we're trying to represent that real world thing that we use 90% of the time when we're trying to glue tables together horizontally, that's how those are the operators that we can use from the world of relational algebra. So we know that the schema returned by this statement, that is, the design of the table returned by this statement, and it has no name really, but we know that it's going to have an ID column from the student schema. It's going to have a name column from the student schema. It's going to have a department name column from the student schema. It's going to have a taught credits column from the student schema, and it's going to have an S underscore ID column from the advisor schema, and it's going to have an I underscore ID column from the advisor column. And all of the rows that we see in this table will have the same value in the ID field as the S_ID field, because that was the predicate that went into creating this table. And I mean, is this a table that we would want to see on our website, on the same page where we're displaying our schedule of classes for the spring semester or something? It's too much information, right? We don't need to know a student's number of credits. We don't necessarily need to know their department name. I mean, this is why we have that, what is the capital Pi? That projection operator, right? This is the projection operator gets rid of all of the columns that we get by default from a Cartesian join, but you know, probably all we care about is student name and the instructor value, right? If we're generating, let's say that the class schedule is a bad example. Let's say that on your student website you were able to see a list of all students and their advisors. I don't know why they would let students see that. Maybe your advisor gets to see a list of all students and their assigned advisors. But again, even your advisor doesn't need all of this. They probably want to see student names and you know which instructor they're associated with. Pretend you are an employee of the university, one of the advisors and deputy, and people are coming into you to see you at the trio office or whatever and ask what classes they should take next semester. You would want to see a list like that, right? So that you could find that person's name on here and then say, okay, well, go to this person to assign your schedule sheet or whatever. Except, is this what you would want to see? Even if you put a sort of projection operator around this thing to say name and I_ID. So just these two columns, right? Is that what you want? I feel like most of you would say no. Luke doesn't want to see student names and instructor star IDs, because instructor star IDs mean nothing to Luke or me for that example. I don't know who to send the student to if I've just got a star ID for an instructor. What do I really want? No, not me. Luke, what do you really want if you are a trio advisor and someone has come in and needs to know who to sign their schedule sheet? Yeah, so we have their ID, but we don't have their name. Where is their name in your database? That's not one of our sources here. That's the problem. We know where the data is, but we're not drawing data from a table that has the data that we want. Luke wants student names and Luke wants instructor names. But, and we have the advisor relationship in here, but the advisor relationship doesn't give us instructor names. We need to add another freaking table to this thing. Can anyone predict what that relational algebra statement is going to look like? I mean, it's going to start with that. We're 2/3 of the way there. And that is basically giving us this table of columns here. All we need to do is attach this table of columns to a table of instructor data, the instructor table, on the basis of what? What values should be the same between those two? I've got like 3 IDs in this table. You're going to have to be way more specific.
The instructor, to get to their name. She got the instructor ID in there, so if you match it to the instructor ID and instructor table,
Yeah,
And you can match.
that's exactly right. So, yeah, let me take this projection thing off here because this table is not yet wide enough. I need more columns. This table I want to attach to the instructor table, which if I had a schema here, it would probably say ID and name and department name and salary or something. And so basically, I'm adding 4 more columns to this thing. ID, oh, it's not unique, and so I'm going to have to say, well, this is the ID that comes from the instructor table, and this is the ID that comes from the student table. Okay, good enough. And then we're going to have, non-unique. This is I.name and S.name. I mean, really, this is, we would type instructor dot and student dot, but I'm just taking shortcuts here. And department name, I.department name. I'm just going to call it department because I'm tired of writing. And finally, salary. I don't need to prepend salary because it's unique. But okay, so now, this is what Access would return, is it's not going to throw out columns. It's just going to, when columns do actually have the same name, it's just going to prepend their source table to the beginning of that column name. And so all the rows from this table will match up together with all of the rows in the instructor table, but I think what Laura was saying was that the value of IID from that original table has to match the value of I.ID that it matches to in the instructor table, so that, we only have the details for the instructor who is the actual, that match the ID of the actual person assigned to be the advisor of this student here. So I'm not quite sure what's about to pop up on this screen, but I assume it's student cross advisor cross instructor, where I.ID is equal to I_ID. And apparently I'm not telling you which table ID is coming from here, but you're probably going to assume that it's student dot capital ID. Does this make sense? Is this what you were thinking, Laura? This guy right here? These two values have to be the same. Oh, I didn't identify that guy either, but I guess if we're just, because I mean, this group table, it has an ID field in it. That's why I really should specify which ID field I'm talking about, because I don't want to match I_ID to the student ID field. So that relational algebra is not as specific as it really needs to be. It would probably fail if we were typing relational algebra statements into our Microsoft Access instead of pointing, clicking, dragging. But this should give us what we want. At least this should contain the information that we want. We have instructor names, we have student names. Really, we don't really want any of the other information that comes with all of that. And so this is where I would take that projection operation. And then I would say, out of all of these guys, I really just want S.name and I.name. Or however the system asks for it, instructor.name and student.name. Because the computer, the database in the background does go through a lot of work matching up all of these rows, only those rows where the values are the same. We can assume that all of that gets done, and it gives us all of these columns, and we only want 2 of those columns, so we can say, oh, great, that's nice work. Only show me these 2 columns. Only project these 2 values. I just want to see student names and instructor names. Those are the things that make sense to me. IDs help the computer do its work. I mean, they are underpinning how all of these rows got put together, but I couldn't for the life of me say what any of your star IDs were. I know I have them in a spreadsheet somewhere, but star IDs mean nothing to me. Someone says Samuel Ogren, okay, I know who that dude is. Mr. Kapisky. All right, well, so just a review of the stuff that we've talked about. Really, everything is just going to be a combination of these operators. We have that selection operator, which grabs stuff out of the named table according to whatever predicate is attached to that operator. So all rows where the salary column has a value greater than or equal to $85,000 is what would come out of the instructor table. In this case, projection, like you saw, takes whatever that table is and then filters out everything except these columns. And it can be as many columns as you want. But projection works that way. You've seen what natural join does, and I mean, at first it looks pretty good. It does a whole lot of work. It joins every row with every row and then throws out every row that don't have matching values on the columns that are common between those two tables. But what if you have two tables that have no columns in common, such as the student table and the advisor table? Natural join wouldn't work on that system, and that's why we need something a little different from natural join, and that's why I added the Cartesian product with predicate operator. Maybe that's, oh, there it is, it's in this table. So, yeah, Cartesian product is a basic, a fundamental relational algebra operator. I think natural join is just built on top of Cartesian product. And so we have 1, 2, 3, 4 basic operators, and then the only fundamental operator that I'm leaving out is the difference, the minus sign operator, just because it's used to form an intersection, but it's not as useful as these guys here. And really, this guy, even though he works really nice, we almost never use bow tie or bow tie, because he assumes that tables that need to be connected will have same name columns, and we just can't rely on that to be true. I feel like I told you guys at some point, I think that this must be a copy of a slide that I already showed you. Maybe, I don't know. But I feel like I already showed you guys the arrow operator, which is also used in relational algebra. It's just a utility operator. It's basically making an exact copy of a table, and we're going to give it a different name. Sometimes that's useful to us. Sometimes we want to connect a table to itself, and so it needs to have a different name in order for us to do that. So when you see me doing something like student arrow A, I'm just making a new copy of the student table, an exact copy, but its name will be A, just so you know I have a second copy that I can connect to, because apparently I need it or something. Make sense? Well, now that we've got our schema diagrams out, let's ask this database system some questions, some queries that might make sense for a university database situation, and let's represent them as relational algebra statements. So, for example, I mean, this is kind of a general question, but if I want to see all of the data about university students in this system described in the schema in front of you, what relational operators do you think you'd use? Adam, what do you think?
I don't remember all of them, I'm gonna be honest. Whichever one grabs the table.
Which is the grabby one?
Selection.
Selection. And what is the name that I'm going to put in the parentheses?
I don't know. Oh, you said students?
Yeah.
Okay, students.
Students. And do I need any kind of predicate there? Did I specify any? No, I'm not specifying any particular student. I want to see them all. I'm selecting everything from the student table. Not gonna show that? Ah, there it is. The selection operator, no predicate, source table is the student table. That makes sense? Mr. Kapinski, is that what you would have written down for the pop quiz? Oh, you know there's a pop quiz coming. All right, well answer me this one then, smart guy. Show me all of the student information for computer science majors. According to your schema, what kind of relational algebra statement would you write for that? Yeah.
Can you go back to the page that is on the list?
I wish you hadn't taken notes of those 5, but okay.
Yeah.
Because see, now I can't see the question anymore. But you remember, show me all the records about computer science students. Is there any information in the student table that can help you with computer science students?
The department name?
Yeah. And I don't know what value they use in that field, but presumably it's a string. You can just make up whatever you want. You can just use the letters, the string, capital C, capital S, and I'll take it on the pop quiz, right?
Okay.
Just tell me what data value it's filtering on. And do you guys agree? Does that make sense? The selection operator, and then the predicate is department name equals CS, and then grab everything from the student table. We're only going to see the rows from the student table where department name value is CS. If we misspell whatever that string is, then we're not going to get anybody, probably. It really depends on what that department name value is, but given the information that we know, which is not very much, we can use any value we need if we need a literal, as long as I can understand what you mean. I mean, if you said department name is equal to biology, I probably wouldn't give you full credit on this one. What if I only wanted to see the names of university students? And I'm apparently not talking about just computer science students. But which table am I going to get that information out from?
Students, again.
Students.
Only select name.
Well, selection doesn't only select. That's another operator. What's the operator that I need to also use in addition to selection?
Projection?
Projection. Because all I care about is the name column, right? And projection filters out columns, other than those columns specified in the predicate. Selection filters out rows that do not match its predicate. So they're both filters of some kind. It's just selection grabs horizontal things, selection grabs rows, and projection filters out vertical things from those. So if I were to build a parenthetical statement where I need to work my way out from the innermost parentheses, probably the innermost thing would be the student table, and I'd have selection select everything from the student table. And for this question, I would put a parentheses around that statement, and I would have a capital pi in front of it, and what would your predicate be for that?
Oh gosh, student table. Names?
Names.
Yeah.
So filter out everything but the names column from select everything from the students table. Right?
Okay.
How would we do that with selection operators and projection operators in parentheses? Would it look something like this? Does this make sense to you? So I'm going to give you guys a homework on building statements like this and telling me what they return. So you might want to take notes. Or I guess, this is probably up on D2L. But, so you can probably find this slide later on. But this is why we're doing this. Eventually, a homework will come along where I'm going to give you this. This is called an intent. This is how we describe between humans what we want from the machine. But machine doesn't understand our language. Machine understands the math language. Machines only do math. I bet you want to do the next one. Are you ready? Are you raring? Oh, you don't have a schema. Oh, good. Perfect. I only want to see the names of computer science majors. I mean, if I were you guys, I'd write down in my notebook what I think that relational algebra statement's going to be, and then see if he comes up with the same answer you do. That's just me, though. Writing is so 1800s.
Wouldn't that just be the same as the last one, you just specify selecting the department name for the students?
Yeah, so tell me what to write on the board if I were writing this. From left to right, what do I start with?
Whatever the name is for that last symbol.
Projection here?
Yeah, that.
Yeah. Projection, and then you're still only grabbing the name column? Okay, projection name parentheses. What's inside the parentheses?
The selection of the department name of students, like on that.
Department name equals what?
Yeah.
Yeah. Does that make sense? Is that what you guys would have written? This right here? Yeah, basically I've just combined those two things that we did above and made it a little bit more specific. Grab all students information, grab only student names, or display only student names. No. Grab only computer science students, then display only student names, then display only computer science student names. Whew. Oh, we still got time. Veda! Veda, 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 Veda. Are you ready?
Yeah.
Ah, perfect. You're the database administrator, and some noob who doesn't even know how to use a computer is coming over to you and says, I want you to get out of this machine all of the names of the people who work on this campus, where your database schema has all of the information about this campus. And so, apparently there are no tables for service personnel or administrators. So who are the names of who are the people that are represented in this database schema? And how can you show me all of these names? I feel bad about this one, but let's give it a shot. Just get me partway there, Beta. Just give me something that will work. Who are the people who work on this campus according to your schema diagram?
Instructor.
Instructors. How do I get all the names of instructors? Selection.
Name. And then in parentheses instructor.
Yeah. So I'm not going to put name here because selection doesn't do columns. But you're right, I do want to grab grab my data out of the instructor table, and all of it is going to come because selection doesn't even look at columns, doesn't care. And so you're telling me that around this, grab everything from instructor, you want to put what out here to just get their names?
Projection.
That projection operator, right? The capital pi. How does capital pi work, Beta? Do you remember? That's where you want to put the name predicate. So this is going to grab all of the names of instructors from campus. Give you a list of them, one column. Aiden. Who else else, what other individuals are on this campus?
Students
All right, so what relational algebra statement do I type in to get all of their names?
so students will pretty much be the same as that, but students instead of restricted.
All right. Grab me all the names out of the table returned by, select everything from the student table. One column of names, one column of names. This is, probably a column of string values, a column of string values. You know what those two columns are? Those two columns are union compatible. If you just want a single column of all string values, all names, you just put the union operator between them, and that concatenates tables vertically, top to bottom, as long as those tables have the same number of columns and they contain the same data type. You can't concatenate a column of integers to a column of strings. But, your database is not paying attention to whether those column values mean the same thing. It doesn't care. And apparently we don't either. All we need is names of people. We don't care if they're names of students or instructors or janitors or electricians or anything. We're just listing all of the names of people in our database. And in this case, that fits whatever question was asked here. I don't know the reason these people ask me questions as the database administrator, but I can get them the answers for the questions that they give me. Maybe they're not the answers that they wanted, but they just need to be more specific in that case, right? In this case, I'm showing them all the names of the people that I can find in this database schema. And I'm returning it to them. Make sense? Any questions? Can we build these? All we have to do is remember like 5 symbols. I'm very rarely going to ask you to use the minus sign symbol. Not for real world stuff. Maybe an assignment just to force you to use the 5th symbol. But otherwise, most of what we're going to do is selections, projections, and probably what's the most well-used operator in database? Probably Cartesian product with a predicate. Joining some tables together. All right, I think that's all the time I have for you today. Thank you very much for your attention. I will see you guys back here on Wednesday. I do want to let you guys know there will be no class next week on Wednesday and Friday. I'm going to be out of town the last half of next week, but we will meet 2 more times this week.